Pretty great. Okay, great. I think I'm still missing one problem set. Did Julia turn hers in, or? I'm sorry?
Uploading now.
Oh, okay, perfect, sweet. So I'll get those graded problem sets up on Canvas later today. And what we're gonna do today. Oh crap! Hold on a second. Boy, today's Wednesday. Feels like a Monday. I didn't quite.
I think that you're on break for the only thing that.
So I should be able to do it really well.
No,
No, I know. Yeah, no. I'm been behind on everything. I'm using this. As break weeks are always a week to catch up, so I've been frantically catching up on a lot of things. And when I saw that I had written out this is what we're gonna do today, the products and quotients, and then looking at the chain rule, I was all right, I'm all set. But I didn't actually check to see that I printed out the notes to OneNote. So let me do that now. It'll take me less than a minute. Perfect. Okay. So last time we looked at some shortcut rules, right, that allow us to not have to set up the limit every time that we find a derivative. We're going to continue with those today. We left off with the product rule, and today we're going to start off looking at the quotient rule, which is quite similar, and then the chain rule. The chain rule is this sort of uber rule that kind of is almost always sort of lurking there, that we are going to need to be aware of, unless our function is particularly simple. Usually the chain rule is involved. So before we start that, I'll take any questions you might have. What's that? Okay, all right. Okay, then let's pick up where we left off. So we did the product rule. Okay, so if we go back up here, the product rule takes on this form, right? Where we're kind of just adding a couple of products together. It tells us how we take the derivative of when I multiply two functions together, right? And we know that we have to use the product rule if both things we're multiplying together have variables in them. And the form is pretty simple, right? We're just kind of adding a couple of products together. We're just taking turns, right, of which function we're taking the derivative of in each of those two products. The quotient rule takes on a similar form. With the product rule, notice that since we're adding these two products, it doesn't really matter if we started with GF prime or FG prime. We're adding them together, so either would work just fine. I always write it in this order, though, putting the GF prime first. And the reason I do that is because the quotient rule, which is really quite similar, involves those two products, right? GF prime and FG prime. But with the quotient rule, we are subtracting those two, right? Subtraction is not commutative, so in order to make sure that I remember which one goes first, I just always write them both out with the GF prime coming first. So the derivative of the quotient f divided by g is gf prime minus fg prime all divided by g squared. Again, this is a rule that you're going to need to know. So when I'm working out quotient rule problems, I usually make sure I write out the rule just straight up before I plug anything in. And that way, when I need to know it, it'll be really difficult for me to forget it because I've written it out about 1,000,000 times. So with the product rule, because multiplication is commutative, it doesn't matter which function we call f and which function we call g. With the quotient rule, it definitely matters. F has to be the one on top and g has to be the one on the bottom. So if we just do a quick example here, we're going to find q prime of x, where q of x is this function. Again, the first step to using the quotient rule is knowing that we need to use the quotient rule. I've got variables in both the top and the bottom. It's a clear sign that I need to use the quotient rule. So my f function is on top, 3 minus 2x. So what is f prime?
1.
Not 1.
Oh,
Yeah, negative 2. Good. And our g function is x squared plus 2. What is g prime?
2x.
2x. Isn't it great that we just get to look at it and say what the derivative is and we don't have to set up a limit? We're all pretty excited about that. Alright, so to find q prime, I'm going to use the quotient rule. I'm just going to write it out fresh. G times f prime minus f times g prime all over g squared. So I could just plug everything in. G times f prime is x squared plus 2 times negative 2 minus f, 3 minus 2x times g prime times 2x, all over g squared. So I'm going to square x squared plus 2. We're going to be really vigilant about our algebra here. We may feel an urge or desire to cancel like the x squared plus 2 here, but we absolutely cannot do that. Could somebody explain to me why we're not allowed to cancel those? Yeah, we've got subtraction up here, right? You're only allowed to cancel when what's on top and what's on bottom is an actual factor. And x squared plus 2 is a factor on the bottom, but it's not a factor of the whole numerator. So we cannot cancel over addition or subtraction. And so the only thing we can do is expand the numerator and then simplify it. So I'm going to distribute that negative 2. So I'm going to minus 2x squared minus 4. I'm going to distribute this 2x, but also this negative through there. So we've got a minus 6x plus 4x squared. The bottom I always leave factored. There's no addition or subtraction, or the only addition and subtraction is happening inside the factor. So like we don't gain anything from expanding out the denominator. And in fact, sometimes it can make it harder to analyze the derivative and see what it tells us. So I always leave that factored. So we have, if we simplify up top, 4x squared. We simplify up top, combining like terms, we have positive 2x squared minus 6x minus 4. And then, I often see if I can't factor, that can lead to insight into the behavior of a function. We could take out a 2, but I don't think that will unfoil. So, whoops, I dropped the square here. X squared plus 2 squared on the bottom. So I think that's as far as this can go. I just want to sort of emphasize, since we talked about it a bit, that once we did our first implementation of the quotient rule, right, we just filled in the G prime F and, F G prime. We expand each product in the numerator. And then we just leave the denominator factored. Let's try another one. Are there questions on this one before we go to the next example? Okay. All right, so this one's an application problem. They tell us that the concentration of a drug in the bloodstream is given by this function. C is a function of time. So it tells us what the concentration is over time, like where T is hours after the drug is taken. And we're going to find dCdt. So we're finding a function that describes how the concentration is changing. If we think about this, before we even start, we might think about what we would expect to find the kind of behavior for the function of the concentration, right? At first you have zero concentration before you've taken it. Then you take the drug and the concentration in the blood goes up, right? Because you went from nothing to having the drug in your bloodstream. Then your body filters it out, so then the concentration starts decreasing. As far as the derivative goes, what would that look like, right? At first, there's no concentration, and then there is some. So it increases, which means the derivative itself starts out positive, and then the body works to get rid of filter out the drug from your bloodstream. And then that means that the concentration is decreasing, so we'll expect that the derivative itself becomes negative during that part of the process. What we're going to do is find the derivative, and then we're going to take a look at the graphs of both C and dCdt and see how they're related to each other. So our function, 25t over t squared plus 5. It is we have to use the quotient rule. I got t's in both the top and the bottom. So our top function, f is always on top, 25t. What is f prime? 25. Our g function on the bottom is t squared plus 5. What is g prime? And now we're going to set up the quotient rule. Oh, whoops. Don't need that one quite so big right here. Just the quotient rule goes gf prime minus fg prime all over g squared. So now we'll fill things in. G times f prime, so that's t squared plus 5 times 25 minus f times g prime, 25t times 2t. This is all divided by the square of the g function. So t squared plus 5 squared. So this is our first go at just applying the quotient rule. We have our raw form of what dCdt looks like. We want to simplify it, so we're going to make sure we expand out the numerator, simplify that as much as we can. We leave the denominator factored. So 25t squared plus 125 minus 50t squared. So combining like terms, we get a negative 25t squared plus 125 over t squared plus 5 squared. And we can take out We can factor out a 25, and I'm actually going to factor out a negative 25 because I like my polynomials to start with a positive term. If I take out a negative 25, then we have t squared minus 5. And, I get to this part, and part of me just feels almost disappointed because, boy, I'd love to be able to cancel something, but nothing cancels. So I've got a t squared minus 5 on top and a t squared plus 5 on the bottom. We did what the problem asked us to do. We found dc dt. So let's take a look at what these graphs look like. So we're gonna, I'll put in the blue function, the first one, I'll put in the original, the given function for c. So that was 25t, which of course we've got to use x's in the calculator, divided by x squared plus 5. And then in red, I'll put the derivative, negative 25 times x squared minus 5 divided by x squared plus 5 squared. Now when I think about graphing this in an appropriate window, t is time, or in this case x is time after the drug is taken. I don't think negative values of x don't really make sense. So I'm going to start my x-axis at 0. I'm not entirely sure what the y scale should be, so I'm going to go up to, like, I don't know, I'll just use the negative 10 to 10 first and see what that looks like, and I might need to make some adjustments. And I'll let x go out to 20, like 20 hours. That seems like a plausible time frame. Let's see what this looks like. So there's, oh, okay. I'm going to adjust the window. We obviously don't have to go down very far, so I'm going to make my y scale just go down to like -2. I'll make my y scale go up to like 7 maybe. Okay. So in blue, that's the concentration, that's C. And as we kind of discussed in the beginning, it starts at 0, the drug is taken, so the concentration increases. It reaches some sort of peak here, and it reaches like a peak value, and the body is working to get rid of it, so then it kind of slowly starts decreasing as your liver and kidneys start working to filter it out. The red graph is the derivative. And it starts, the derivative itself is decreasing, but what we notice here is that the red graph is positive, right? The values for which the blue graph is increasing correspond to the values for which the red graph is just above the y-axis. And that makes sense, right? The derivative is positive there. Here, the blue graph, where it kind of peaks, if we were to draw tangent lines, right, at that point, the slope would be 0, right? It would have a horizontal tangent line. That corresponds, where it peaks, corresponds precisely to where the red graph crosses the x-axis, where the derivative itself is 0. And where it turns from increasing to decreasing, we can see the red graph turns from positive to negative. So there's, these two graphs sort of complement each other. In a way, the red graph kind of helps to describe the behavior of the blue graph. We're going to do a lot of curve sketching later in the semester. It's everybody's favorite topic, but it kind of challenges us to really think about how the derivative is related to the function, how it tells us about the behavior of a function, and we're just kind of getting a kind of a peek into that when we compare these two graphs here. Are there questions on that example? Okay. Then let's talk about the chain rule. The chain rule is sort of simple to state, but it's just huge in terms of its impact and what it allows us to do. You know, the power rule so far of what we've learned is like helps us find the derivative of a polynomial, x raised to a power. If we're dividing some expressions with x, we can use the quotient rule. The chain rule takes our regular rules and it really expands and opens up the field to more types of functions. And it really talks about how we find the derivative of a composition of functions. When maybe I don't just have x raised to a power, but I have stuff raised to a power. Like maybe I've got 3x minus 7 all raised to a power. And I can still use the power rule on those parentheses to a power if I apply the chain rule. The way the chain rule is stated is simple enough. Is that dy dx, like if I have y as a function of u and u is a function of x, right? So that in a sense y is f of g of x. It's not just a function of x, but it's a function of like some stuff, right? I've got like some meat in that. Then dy dx is dy du times du dx, meaning you see how y changes with respect to u, and then multiply that by how u changes with respect to x. Algebraically, it works out so simple. Like it seems like it ought to be true, right? Like can't we just cancel these du's? And basically that's what the chain rule kind of says that we can do. So this is a general statement of the chain rule for any type of composition. Here's how we're going to experience it at first. We're going to see it in other venues later. But for us, the major rule that we have right now is the power rule, right? We have the product and quotient rule too, but like the biggest rule that we have that's sort of governing everything is the power rule. So here's the general power rule, which is just a restatement of what we already know. But maybe I don't just have x to a power, maybe I have some stuff to a power. So if I have y equals u to the n, so u is just some function of x. If I have stuff raised to a power, the general power rule says I can use the power rule as normal, that's this first part, right? As long as I remember to multiply by the derivative of the stuff. This part where we do times du dx, that's really us implementing the chain rule. I'm going to start out, when doing this next example, I'm going to do this example twice. I'm going to do it once by using this language and notation of finding some u's, what's our u in this case, and then I'll just sort of do it again in terms of like how we often just implement this rule. But if we look at Theorem 5 and the general power rule, the u function here is 3 minus 5x squared. So that y is really u to the 7th. Now, the general power rule says that dy dx, I can apply the power rule like I normally would here, right? U to the 7th. I would take the 7 down times u to the 6th. But now the power rule says times du dx. That's where I go over here and I say, okay, u is 3 minus 5x squared. So that is a du dx. What do we get for du dx here? Yeah. Good. So I know what du dx is. I know that u is 3 minus 5x squared. And now I'm just going to substitute these in. And just simplify a little bit. So 7 times negative 10x is negative 70x, and then times 3 minus 5x squared to the 6. The chain rule makes it so that I don't have to think about, well, what is 3 minus 5x squared to the 7th? Like, I'm not foiling that out, all right? Like, I don't want to. That's awful to do, and it probably leads to some, it's really easy to make some errors just because it's a long, arduous process. But the chain rule says, look, I've got stuff to a power. I could still just use the general power rule. I could still use the power rule. I just have to remember to multiply by du dx. Now, I said I was going to do it twice. And really, either of these two approaches is fine. As you do more of them, you'll probably, just might start gravitating toward this approach, which is just recognizing we have stuff to a power, right? I've got parentheses to a power. I'm not going to write out what u is or anything. Like, I'm just going to say, oh, look, I've got some stuff to a power. When I want to find dy dx, I can use the power rule like I really want to, right? It just seems like I ought to be able to do it. I can do it. Bring the 7 down. And then I rewrite the stuff as is, no changes, 3 minus 5x squared to the 1 less power, and follow up with the derivative of what's inside, which is minus 10x. And then, of course, now we're back to where we were over there. Are there questions on that example? Okay. All right. Now, the chain rule is great. We have to exercise some caution whenever we have a function that requires us to combine the chain rule with either a product or quotient rule. There's going to be what appears to be a lot of algebra involved, and there is, like, a bit of algebra involved, but with these types of problems, the type of algebra always works the same way. So if you do a bunch of practice, you kind of know what to expect. So the first step in using the product rule is understanding and recognizing that we need to use the product rule, right? So I have 3x squared times 2 plus x to the 4th all to the 5th. So we have, like, here's my f function and here's my g function. They both have x's, so I have to make sure I use the product rule. My f function, 3x squared. What is f prime? 6x. Our g function is 2 plus x to the 4th all to the 5th power. What is g prime? Here's our new rule. Or maybe not the finished product of g prime, but like what's the process? Like, what do we do to get g prime? Or who wants to start us off?
Bring down the power of 5.
Mm-hmm.
Then write 2 plus 4 to the 4th power.
Yep.
Times with 4x.
Close. Times it by what?
4x to the 3rd.
Yeah, great. And now I'm just going to simplify a little, right? So we got 20x cubed times 2 plus x to the 4th all to the 4th. All right, so we have ourselves set up nicely here. R prime of x is g times f prime plus f times g prime. g times f prime, 2 plus x to the fourth all to the fifth times 6x plus f times g prime, that's 3x squared times 20x cubed, 2 plus x to the fourth all to the fourth. There is some algebra to do to simplify this, and it does not involve expanding everything out. So, I think maybe I'm going to do one step before we do the big simplifying. I'm going to just, this 3x squared times 20x cubed, I'm just going to multiply those together. All right, so the simplifying step does not involve multiplying things out. It actually involves factoring. And we're going to factor out a greatest common factor. Now, if we look at, like, this part, right, that I've highlighted in yellow, I think we can see pretty clearly they both have a 6 and they both have a factor of x. And x to the first is the highest power of x, you know, that they have in common, so we're going to include that. But they also have these the 2 plus x to the fourth in common. They have the 2 plus x to the fourth in common. The only difference is they're being raised to different powers. And when you factor out a common factor, you always take out the least power that they have in common. So that's 2 plus x to the fourth all to the fourth power. So we're going to take that out. So 6x times 2 plus x to the fourth power. Open up a set of brackets or parentheses. And now we're going to figure out what do we need inside. So we took out the 6x. You know, so let's say we're focusing on the first term, right? In the green box here. I took out the 6x, so I don't need that at all. That's gone. But I took out 2 plus x to the fourth power, but this is to the fifth power. So I need a 2 plus x to the fourth to the first power. And usually we would leave off writing to the first power because, you know, we don't have to write it, but I'm including that right now just to kind of emphasize how we came across that first term. Now if we look at the next term in the blue box, what do you think we need to pick up, you know, to make that term whole? Yeah. We don't need the 2 plus x to the fourth. We don't need the parentheses at all because I took out the fourth power and that is the fourth power. The only thing left to do now is simplify the stuff in the brackets. But I want to just emphasize, I just want to kind of see what happened here. In one of the terms in the brackets, if you look at in the what we ended up putting in the brackets, in one of the terms we needed 2 plus x to the fourth to the first power, and in the other term we didn't need it at all. It always happens that way when we're combining the chain rule with the product or quotient rule, because if you look at the quotient rule, or in this case, the product rule, it was, actually I guess it was the g function and g prime that had the parentheses. So in one function I have g, in the other I have g prime. They will, because of how the power rule works, the parentheses, the exponent on the parentheses will differ by 1. But always, right? Just because of how these, you know, how the g and the g prime come about, the way the power rule works. So when, you know, sometimes people get turned off a little bit or overwhelmed with like the algebra and the simplifying process. But if you do several of these, you'll see that it always kind of works the same way. The only thing left to do now is to simplify what's in the brackets. The parentheses to the first power, we don't need the first power, we don't need the parentheses, in fact, right? Because we're just raising it to the first power. So that is, we have some like terms we can combine. And we have 11x to the fourth plus 2. Questions on that example? Okay. All right. So what's cool about the general power rule is that it also works. It doesn't just work on positive integer powers. It works on negative exponents. It works on rational exponents. So we can find dy dx if y is the square root of x squared plus 1. The first step in using the general power rule is recognizing when you can use the general power rule, right? I can rewrite this function. What exponent does the square root correspond to? Yeah. So this is x squared plus 1 to the 1/2 power. And if we were to apply the general power rule, like how does that start? Who wants to start us off on that process?
One.
Say that again.
Then it would be 2x to the fifth.
Well, so you took the derivative of what's inside? That's what comes at the end, right? When we apply the chain rule. What goes in the parentheses?
Goes x squared plus 1.
Yeah, right. We don't make any changes at all first. And what's the power?
Would it be negative somehow?
Mm-hmm. Yep, and it's negative 1/2 because it's just 1/2 minus 1. Cool. Now we're just going to simplify. So 2 times 1/2, those cancel. So we have x times x squared plus 1 to the negative 1/2. We could leave it that way. I'll note that they use radicals in the when they gave the original function. And usually it's nice to avoid negative exponents anyway. So I would call this either x divided by x squared plus 1 to the positive 1/2 or x over the square root of x squared plus 1. And either is fine. Questions? Okay. You know, there's like a theme in a lot of calculus. It's something you're going to hear me say like probably 1,000 times in this during this semester, and that is that an ounce of algebra is worth a pound of calculus. Sometimes we can make our work a lot easier just by rewriting a function. For example, this function, y equals 4 times the cube root of x squared. There's 2 different ways we could rewrite it. And, you know, one of them I would argue is a bit simpler to execute than the other. Just a bit. It's not like a huge thing. Sometimes the gain we get from the algebra that we could do is substantial. Sometimes the gain is just, you know, I guess a little bit. But I would argue, I would point out that there's 2 ways we could look at this function. We could say that this is 4 times let's see, x squared to the third power, so we have parentheses to, sorry, not third, 1/3 power. So we have, you know, parentheses to a power. If we find dy dx this way, let's see, we have a factor of 4 we're going to bring down with us. The power rule says bring the 1/3 down. Then we have x squared to the 1 less power. 1/3 minus 1 is a negative 2/3. And then we have to apply the chain rule, times 2x. So let's see, the coefficients, that's 8/3. 8/3 x times x to the, now I'm going to simplify that power. There'd be a negative 4/3. Now this is x to the first times x to the negative 4/3. Now I'm going to use my rules of exponents. We got 1 plus negative 4/3 is negative 1/3. And then if we use radical notation like they did in the problem, we could call this 8/3 times the cube root of x. Doable, right? Took several steps, but nothing too hairy. We just have to be, you know, mindful of our rules of exponents. You know, remember to apply the chain rule here. Another way we could have rewritten the function to begin with is just to say, well, the cube root of x squared, I could just write that as x to the 3/2. Sorry, 2/3. Right, with a fraction exponent, the denominator tells you what root you're taking, the numerator in the exponent tells you what power you're raising it to. And here, there's no chain rule that I need to really worry about. I just have 4 times 2/3 x to the, let's see, 2/3 minus 1 is negative 1/3. And then we, you know, then we're pretty much done. So we save ourselves a little bit of work by choosing to write it that way. Versus the other way. But I'll point out that they both get you to the same correct answer. Right? It's not like, you know, I guess what's at stake if you don't maybe choose the path of least resistance, or the easiest path, is that you maybe spend a couple more minutes on a problem. It's not that big a deal. There are some problems where maybe our work is shortened quite a bit by making a good algebraic choice. Are there questions on that example? So here's one where I think that this is just begging us to do some algebra to rewrite it. If we look at this, you know, this function is a fraction. So we might think, oh, quotient rule. And the quotient rule will absolutely work just fine, where f is the constant function 1 and g is the bottom. However, if I rewrite it, you know, something raised to a power in the bottom, it corresponds to a negative exponent if we bring it up. So I could rewrite this as 1 minus 4x to the negative 5th power. This is what I might describe as power rule friendly. Because now, you know, a lot of times when we have a function that's a fraction, if I choose to bring the bottom up and write it to a negative exponent, that might just change a quotient rule problem to a power rule problem, and it doesn't really save us a lot of work. But here, because the numerator had no variables, there's no x's up there, it was just a constant, it really does make it, I don't have to use a quotient rule or product rule. I only need to use that general power rule here. So if we start out finding f prime of x, who wants to get us started? What does it look like?
-5.
One minus four.
Yeah, to the -6 power, we're subtracting 1. And then what?
Times 4.
Times... Sorry, say that again?
-4.
Yep. Cool. And then simplifying, we have a positive 20 times 1 minus 4x to the -6. It is conventional and good practice, I think, to avoid negative exponents, so I'm going to write this back in the form of a fraction. Negative exponents can be your friend when it comes to rewriting a function to make it easier to take the derivative. When it comes to stating the answer, I almost always adhere to the convention of avoiding negative exponents, especially when I'm doing like calculus or like, you know, if I'm finding a derivative and, you know, ultimately what we're leading to is like using the derivative to help us solve problems, like to give us insight into the behavior of a function. One of the types of questions that we ask ourselves a lot in calculus is, where is the derivative equal to 0? Right? As it turns out, that's a really insightful question to ask that can tell you a lot about the behavior of a function. It can help you solve some problems if you're trying to maximize or minimize something, and we'll do a bunch of that in the next chapter. But I just want to point out that with the function written in this form here, as we wrote it as a fraction, right, with no negative exponents, it takes me 1 or 2 microseconds to look at that and say, oh, it's never 0, right? A fraction is only 0 when the numerator is, and 20 is never equal to 0. So I know that that's never 0. And when we leave negative exponents, we can be tempted to think, oh, well, something's 0 when either of its factors is, so I'm going to set 1 minus 4x equal to 0, and that'll tell me where the function itself is 0. In fact, that won't tell me where the function is 0. It'll tell me where the derivative is undefined, right? That'll tell me where I'd be dividing by 0. So it is good practice to avoid negative exponents in your final answers. Are there questions on that example? Okay. Let's do one more. We're going to find the derivative of this function, x divided by the square root of 1 minus 4x, and then we're going to evaluate it when x is -2. Let's take a look at this function, at its structure, like its overall structure of this function. What do we have to use to help us find this derivative? Say that again. I don't know if you said it and I just didn't catch it, but yeah, okay. Sometimes the sound cuts out a little bit, and I apologize for that. This is a quotient rule, and it's not one that we can avoid. We have x's on both top and bottom. At best, and I don't even know if I'd call it at best, but like the only thing we would do by rewriting it as a product with a negative exponent is changing a quotient rule to a product rule, and that doesn't really save any work. So we have a quotient rule here. And so that means our f function is always on top. F is equal to x. That means f prime is just 1. What is our g function? Like, how do I want to write it in order to help me take the derivative?
One minus 4x, 1/2.
Yeah, good. Now, And it's to the positive 1/2, because with the quotient rule, it is just as it appears on the bottom, right? The function as it appears on the bottom. If I rewrote it as a product, right, then I'd have a negative 1/2 power. But if I'm using the quotient rule, it is the positive 1/2 power. If we find G prime, who wants to start us out with that process?
One half times 1 times 4x to the negative 1/2. Times negative 4.
Yeah. Great, so we have -2. Now this time, when I find G prime, I'm going to leave the negative exponent. This is not my final answer, right, for the whole thing. I'm leaving the negative exponent here because it's going to help me with the simplifying process later. So when we find dy dx, it's a quotient rule, so I'm just going to write out the quotient rule first. G times f prime minus f times g prime all over g squared. So g is 1 minus 4x to the 1/2 times f prime, which is just 1, minus f, which is x, times -2, 1 minus 4x to the negative 1/2. This is all over the square root of 1 minus 4x squared. I'll do a little bit of simplifying. So first of all, on the bottom, I'm squaring a square root, so that's just 1 minus 4x. On top, I have 1 minus 4x to the 1/2, and then I guess that's a plus 2x. So 1 minus 4x to the negative 1/2. So this is one of these problems where we are combining in this case, a quotient rule together with a chain rule. So we have that simplifying step that involves factoring out the greatest common factor. And what is the greatest common factor of the top?
One minus 4x to the 1/2.
You're almost there. When we find or identify the greatest common factor, we compare the powers, and we always take the least power. So in this case, that means we're going to take out a negative 1/2. So we take out a 1 minus 4x to the negative 1/2. I'm going to open up a set of brackets. So we're going to start with this first term here. What do we need to make that whole?
1 minus 4x to the negative
1 minus 4x. So if it's to the negative 1/2, if I were to multiply these, imagine that we were distributing and maybe going backwards, right? If I multiply those two together, 1 minus 4x to the negative 1/2 times 1 minus 4x to the negative 1/2, what do we get?
negative 1/4.
Say that again?
The negative second power.
It wouldn't be we'd add the exponents, right? Negative 1/2 plus negative 1/2 is negative 1. It would give me the negative 1 power. What I want is the positive 1/2 power. So in order to get the positive 1/2 power, what I need to ask myself is what goes here so that when I add it to negative 1/2, I get positive 1/2. 1, positive 1. And in fact, that is always how these work, right? Think about how the 1 minus 4x to the power appears in the products above here, right? In one of those products, I had just plain old g, and in the other product, I had g prime. Those powers will always differ by 1 because of how the power rule works. So this is just to the first power, and then plus. Now what do we need to make this term whole?
2x.
Just 2x. Yeah, good. And we got a couple of things we can do here. One is we have like terms in the brackets. We can simplify, just combine the like terms in the brackets to simplify that. And then we have this stuff to the negative 1/2 power. I'm going to throw that downstairs to the positive 1/2 power. Up top, we have 1 minus 2x if I combine the like terms. And now we're almost done. I'm just gonna, we have the same base on the bottom, so I'm just gonna add those exponents. So we have 1 minus 2x over 1 minus 4x, and if I take 1/2 plus 1, that's 3/2 power. So this is dy dx. So that's part of what they asked us to find. Then they wanted us to evaluate this at 2, but I'm going to stop here for a second and just see if there are questions on the process that we went through. And like the setup, or like how, the algebra we did to simplify this. Okay. Great. So, I guess let's evaluate it at -2. So let's see, that's 1 plus 4. We get 5 up top. On the bottom, that's 1 plus 8, so 9 to the 3/2. The 3/2 power means take the square root and then cube it, so that would be 3 cubed, or 27. So we get 5 over 27. Okay. Are there questions on this example before I talk a little bit about what to expect on your quiz Friday? All right. So I know Friday you have a short day. So there will be 3 questions. One question will be finding dy dx using a limit definition. But it'll be limited to like a quadratic. Like it's not going to be a fraction or a radical or anything super complicated. Nothing more complicated than a quadratic. So something you can do some expanding on and then set up that limit and evaluate. And then 2 questions on finding, find dy dx, find a derivative using our shortcut like power rule or chain rule or product rule or quotient rule. And we do have class tomorrow. We're meeting tomorrow, so tomorrow we're going to kind of keep doing some new stuff. What we do tomorrow is going to be related to what we did today. We're going to look at implicit differentiation. I'm not going to do any more than just one section tomorrow, because I want to make sure there's plenty of time for questions that you might have. I want you to give yourself time to like get some practice exercises done. And just come with whatever questions. If there was a problem you found difficult or that you get stuck on, or that you weren't able to finish or something, let me know. We'll spend some time going over questions you have before we talk about implicit differentiation. Are there any questions, any outstanding questions before we adjourn for the day? Okay. All right. Then I will see you all tomorrow morning.
Thank you.